So today's speaker is Alfred de Win, and he's a research engineer too in the High Altitude Observatory of NCAR. And Alfred received his master's degree in physics, astrophysics, and mathematics, and his PhD in astrophysics in 2006 from Utrecht University in the Netherlands. And Alfred's research has focused on observations of dynamics and magnetism in the solar atmosphere, with particular interest in the solar chromosphere. Over the last decade, Alfred has directed his attention mostly to the development of instruments for solar observations, and he is an instrument scientist for the Cosmo K coronagraph deployed at NCAR's Mauna Loa Solar Observatory and for the visible spectral polarimeter on the Daniel K. Inouye Solar Telescope. And he is also the PI of the Cosmo Chromosphere and Prominence Magnetometer, currently in final stages of construction. And he will present today on ViSP and ChroMag. So go ahead, Alfred.
All right, thanks, Nick. All right, it's been a long day already, but here we go. So I'd like to start my talk with a little bit of a history of solar magnetometry. We've really been looking at the sun and the magnetic field in the sun for a really, really long time. Peter Zeeman discovered the well-known Zeeman effect in 1896. He noticed that spectral lines were split in the presence of a magnetic field. And this was sort of a Friday afternoon experiment where he was actually working on something else, and he tried something and saw something interesting, and that turned out to be the Zeeman effect. Curiously enough, splitting of spectral lines had been observed in solar spectra by Young in 1892 already. So that was kind of the first indication that there was magnetic field in the solar atmosphere. Now, Zeeman probably didn't know that, but HAO certainly did, and he built a very primitive spectral polarimeter and looked at sunspots in 1908, so more than 100 years ago, and determined that there was strong magnetic field in sunspots. Now, obviously, back then, they were able to do qualitative diagnostics of magnetic field using these kinds of devices, but quantitative magnetometry really became possible when we developed digital sensors and we had increases in computing power that enabled us to process our observations and determine quantitative numbers on plasma parameters in the solar atmosphere. That really sort of started in the late 70s, early 80s. Instruments that come to mind are the Stokes polarimeters that were built here at HAO by people like Bruce Leitz and David Elmore, who I think I just saw in one of the attendees here. So welcome, Dave. Good to see you. Spectral polarimeters have become very common nowadays at observatories. They're very powerful instruments and very important in our ability to diagnose magnetic field and other plasma parameters in the solar atmosphere that help us solve science problems. As a result, almost every observatory nowadays is outfitted with some sort of spectral polarimeter. They've become so common, in fact, that they're also now in space. Two good examples are the Hinode spectral polarimeter, part of the Solar Optical Telescope on that mission. Here's an example observation of a sunspot from SOT-SP. So this is actually a slit spectrograph, so it's rastered this image from left to right using a slit that moves over the sun, and it has full spectral information and polarization information at every location, and we can use that information then to infer the magnetic field. And here's an example of that same sunspot. Blue is strong field, red is basically field free. Now I'm using the term magnetic field here a little bit liberally. Really what we're more often inferring is magnetic flux density, but I'm going to use those two terms essentially interchangeably in this talk. At the same time, or later, I should say, we launched this Solar Dynamics Observatory with the HMI instrument on board, and this is an observation from that instrument, which shows the entire sun. And that instrument takes data at a very regular cadence, but every 12 or 15 minutes or so, it produces one of these images that has the full vector magnetic field of the solar photosphere over the entire solar disk. So during this talk, it's going to do that a couple times. That's pretty impressive. And we can then use these kinds of measurements to try and do something else. So if we look at the higher layers of the solar atmosphere here, we're looking at the solar corona at about 1,000,000 Kelvin or so. We can see structures that indicate to us, at least, at first glance, that there must be some sort of magnetic field there that structures structures, the plasma. And we can try to take that photospheric magnetic field that we had and extrapolate it into the corona in various ways and produce figures like these. And this looks pretty good, but if we actually were to look at this in some high detail, we're going to notice that there's issues with this. These extrapolations are actually not very good, as it turns out. And it turns out that the photospheric magnetic field doesn't really couple very trivially to the coronal magnetic field and to the heliosphere. That's something that we'd like to do something about, and that's what I'm going to be talking about with the instruments that that this talk is about, ViSP and ChroMag. Both of those instruments are really designed and intended to study specifically these kinds of problems, but they're going to study them in very different ways. And part of the thing that I'd like to talk about today is how these instruments differ and why they ended up looking the way that they did. But continuing on with diagnostics of solar magnetic fields, we can really we can talk about solar magnetic field diagnostics in two broad categories: qualitative measurements such as proximate magnetometry and magnetograms. That's a very relatively simple thing to do. You can think of things like the famous butterfly diagram. I'll show you an example of that. Or this here is showing a movie of the solar photosphere and the low chromosphere. And you can see little bright areas that move around. We know that those are associated with the magnetic field. And so if we can trace those elements, those little bright spots, then we know that the magnetic field is moving around in certain ways, and we can use that to study the magnetic field. Sunspots are another example. Here is the famous butterfly diagram that shows the locations of sunspots and that reveals the 11-year solar cycle. So that's proximate magnetometry. It's a very simple method of studying magnetic field, but it's a qualitative measurement. We don't know how strong the magnetic field is. We don't know its inclination, and many properties are really not known. It's also there's also some other problems with it. And magnetograms are the next step up, and these still have some of the problems. I'll highlight one of those in just a little bit. Here's a movie taken with the Hinode mission. This was actually using a filtergram instrument that had a polarimeter on it as well. And this is showing you line of sight magnetic fields in white and black coming towards you and going away from you. We can then use segmentation algorithms to split these things out and find places where we have magnetic field, and we can try to trace those concentrations. Now, what you might see here is that the magnetic field concentrations are appearing and disappearing kind of randomly across the field of view. And this is a problem with these kinds of qualitative diagnostics, is that we don't really know what happens to the magnetic field when it drops below our detection threshold. We don't really know how strong it is when it is above our detection threshold. So it's easy to use this. It's an easy thing to do, and it's good to use it for qualitative things. But for quantitative diagnostics, we're going to have to do a little better than that. So to do that, we're going to talk a little bit about polarimetry now. So light is polarized, and polarization essentially just describes the orientation of the electromagnetic wave and the phase between the electric and magnetic components of the wave. Now, it turns out that polarization is affected by the physical circumstances under which the light was created, or when it last had an interaction. I'm showing you here below the two figures. On the left is a picture taken without a polarizer that shows kind of brighter areas where light reflects off the water. On the right, a polarizer has been added and oriented in such a way to block the polarization that's created by that reflection. As a result, you can see many more details. So we can use this mechanism because in the solar atmosphere, we also have sources of anisotropy that create polarization, namely the magnetic field. Now, every photon is fully polarized, and we're generally looking at incoherent sources. And so an incoherent source consists of many fully polarized sources, but together those can be partially polarized. And we typically use the Stokes formalism in astrophysics and heliophysics to describe our measurements. And the Stokes formalism describes the light in a 4-vector of intensity, 2 linear polarizations, and 1 circular polarization. They're shown down here below. The 2 linear polarizations are plus Q horizontal, minus Q vertical, and plus U at 45-degree angles, plus or minus U, and circular polarization, plus or minus V. This is a convention. The orientation of the linear polarization is effectively a free parameter. You can choose that however you choose to do it. We generally pick this convention for our measurements. So the next question then is, well, if we can observe the sun and in full polarization, how do we actually then determine a magnetic field from our measurements? So what we're going to do is we're going to observe the sun in spectral lines that we know are sensitive to magnetic field, and we're going to retrieve the magnetic field by a process that we call inversion. I think it's a little bit of a misnomer because there isn't really an inversion process here. It's more of a forward modeling approach. I've included a spectrum here of the well-known iron lines. There's 2 iron lines around 630.2 nanometers. These are the lines that are used in the Hanodian mission, and they've been used on the ground extensively for magnetic field diagnostics of the solar photosphere. What you can see is that there is a very typical antisymmetric signal in Stokes V over here, and symmetric signals in Stokes Q and U. This is expected kind of signal from the Zeeman effect, and what we can then do is try to infer from these measurements what the magnetic field was that gave rise to this particular spectrum. There's also a sunspot here. You can see this. This is a spectrum. The wavelength is on the horizontal axis, and the spatial axis along the slit is on the vertical axis. So this goes from an area of somewhat quiet sun into a sunspot and back out into more quiet sun where there is less magnetic field. So how do we measure that? Well, detectors are 2-dimensional, but our observational space is 3-dimensional. We have 2 spatials and 1 spectral dimension. So we're going to have to slice this cube in some way. In the example that I just showed, we were using a spectrograph. Another option is to use a wavelength tunable imager and then scan in wavelength rather than with a spectrograph, with a slit spectrograph, where we scan in the spatial direction. Now we can try to be clever, and a lot of people have done this. Things like image slicers and integral field units with fibers have been used on instruments. One great example is the DL-NIRSP instrument on DKIS that is currently becoming available. It has a small field of view, but ultimately you're limited by the number of pixels that you have. If we were to look at the visible spectral polarimeter and we made a map of the full field of view with 0.04 arcseconds spatial sampling, which is twice the diffraction limit of the telescope, we would need 18 gigapixels to capture all those all the pixels, all the information. We don't have cameras that are anywhere near that large, so ultimately we're limited essentially by the number of pixels on our camera and how fast we can run those cameras and how much light we can get there. Then the next problem is that detectors are sensitive to intensity. They're not sensitive to polarization. So we have to somehow encode our Stokes vector into intensity measurements and then decode it from those observations. So polarimetry is by necessity a difference measurement. This is actually very good because difference measurements tend to subtract out a lot of systematic effects. So it's typically easier to have a better difference measurement than an absolute measurement. Now, polarization signals, this is good for us because polarization signals tend to be very small compared to intensity. So if we're going to observe these very small signals, it's nice to be able to subtract at least a number of systematic effects out of our data. I'll get to that in a little bit as well, because there are some problems with atmospheric seeing that can cause great issues for polarization measurements. Now, let's say that we have some data and we're going to interpret this data somehow. So I mentioned before that we have this process called that we call an inversion, but the actual inversion process, so that is to say, take measurements, process them somehow, and get an answer, in a direct way is not tractable. So we instead solve a forward problem. We're going to synthesize a line. We're going to compare that synthesis with our observations, and then we're going to repeat that until we find a match. The simplest method that we use for this is called the Milne-Ellington approximation. It's applicable in many cases, and particularly in the solar photosphere, and it's used extensively both for the Hinode SP and SDO-HMI measurements. Essentially, the process is shown below. We have a model with some number of parameters from which we use a radiative transfer calculation to calculate a radiation output that we then compare with our observations. If we don't have a good match, we're going to change our parameters a little bit and try again, and so on and so forth until we get a good match. This works reasonably well, particularly in cases like with the Milne-Ellington approximation, where a number of the parameters we can typically already kind of infer from heuristics or simple formula that are applied to our observations to kind of get close to the solution that we're looking for. Now, the photosphere is kind of the deepest layers of the sun that we can observe. The photosphere is called the photosphere because most of the sunlight escapes from there. But above that, we have a set of other layers that we're actually very interested in because, as I mentioned, the photosphere doesn't couple very well to the heliosphere. So the layers above there, the lower chromosphere and upper chromosphere, separated out here, I wouldn't necessarily do that. That's a very interesting layer because in the photosphere, the plasma is much stronger than the magnetic field, but in the corona, the magnetic field is much stronger than the plasma. So somewhere between, there is a region where the plasma forces and the magnetic forces are more or less equal. That turns out to be the chromosphere. In addition, the chromosphere is driven by the fast dynamics of the photosphere. So not only do we have a highly structured environment that's structured by the magnetic field, we also have a very dynamic region that's being or is being driven essentially from below by the photospheric, the boiling convection that we have in the photosphere. Then above the chromosphere is a very thin layer called the transition region where the temperature suddenly increases dramatically, and then above that is the corona that connects to the rest of the heliosphere, again with much higher temperatures than the chromosphere. The chromosphere is actually pretty cool, and that's not great because it means it's dim, and that makes it harder to observe. Like I mentioned, the chromosphere is actually very important for our understanding of the outer solar atmosphere. As I mentioned, it's where the plasma magnetic field forces are approximately equal. So we know the coronal structure is more or less completely dominated by magnetic field. And we know that it connects very poorly to the photosphere. On the right here, I've shown a figure from a paper by Iijima and Yokoyama from 2017, where they did a simulation. At the bottom, you can see the photospheric magnetic field. At the top, you can see what the magnetic field is like in the corona. And I've blurred out the area in between, which is where the chromosphere is. Now, if I were to give you the both of these inputs, both the photospheric magnetic field and the chromospheric, and the coronal magnetic field, and challenge you to tell me what the chromospheric magnetic field was and how these two are connected, you probably wouldn't come up with this particular solution. So there's a lot of stuff that happens in the chromosphere, and this is very important in our understanding of solar activity, in particular flares, CMEs, etc. A lot of the energy that drives flares and CMEs is stored in the chromosphere. Again, the very poor connection between the photosphere and the corona means that even if we know very well what the photospheric magnetic field is, we don't really know what the coronal magnetic field is, and that makes it very hard to predict what flares and CMEs are actually going to do. So we need to really work towards diagnosing magnetic field in the chromosphere. But this is hard, and that's part of the reason why it really hasn't been done extensively. So what are the challenges for chromospheric diagnostics? Well, instead of just simple absorption and re-emission, scattering of radiation becomes a dominant process, and we can't assume local thermal equilibrium anymore. The photons that are in our radiation field at any location are not created locally, they're created elsewhere and scattered towards that place. That makes it much harder to do this radiative transfer calculation to create the radiation output that we need to compare with our observations. Instead of the relatively simple thing that I showed before, the graph now essentially looks like this, where we have a model that may or may not be correct anymore, with many more parameters typically. We need to calculate statistical equilibrium, which impacts the radiative transfer calculation, and the radiation output, which impacts statistical equilibrium. So we now have a consistency loop that we need to solve. So computationally, this is much harder. Then there's other issues. Because of density and temperature gradients, there are other sources of anisotropy in the radiation, and these cause population level imbalances. So effectively what happens is that the radiation that the atom produces is naturally polarized, even if there's no magnetic field present. As it turns out, there's actually another effect called the Hundley effect, which modifies this polarization signature, and we can use this effect to try and diagnose weaker magnetic fields than we would be able to diagnose with the Zeeman effect. The Hundley effect is in particular important in it's a scattering polarization effect, so you need scattering in order for this to happen. So it's an important effect to study particularly limb structures. So for prominences that extend over the limb and the corona that we observe off the limb of the sun, the Hundley effect is a very important diagnostic to use to diagnose magnetic field. So for chromospheric diagnostics, combinations of Zeeman and Hundley diagnostics offer great potential, but it's much more expensive computationally to calculate the synthetic line profiles from these these diagnostics. And particularly the atomic polarization means that you need a much more complex atomic model, which requires much more computations in order to evaluate and to determine the atomic levels that are required to synthesize the line profiles. Other ways that we can help ourselves is by using many line diagnostics. These tend to constrain inversion results. In fact, we've been doing this for a really long time. The HAO SP, there's a reason why it observes the 630.15 and 630.25 nanometer lines. These two lines are very similar in how they form and where in the atmosphere they form, but they have different responses to magnetic field. As a result, we can use that information and we can compare the signatures that we see in the two lines to resolve the ambiguity between the field strength and the filling factor of that field. You might imagine that if you didn't have that ability to do so, a field that's very strong but fills a very small area of your pixel would produce very similar observations to a field that's very weak but fills your entire pixel. So that ambiguity can be removed by using multi-line diagnostics, and we can try to use such techniques also for chromospheric diagnostics. In recent years, people have worked on developing sophisticated inversion codes for coupled inversions of many lines, and also with non-LTE, so non-local thermal equilibrium effects. Two good examples are the STIC code that was developed by Jaime de la Cruz Rodriguez in Stockholm, and Desire that was developed by Han Uiterboek and collaborators. Both of these codes work in very similar ways, and I wouldn't necessarily have a preference of one over the other, but they're non-trivial to use, so they're still pretty hard to set up, and you have to be very careful with how you interpret your results. Combined Hundley and Zeeman diagnostics are also something that is very important. Obviously, we need these kinds of diagnostics to determine the weaker magnetic fields that are accessible through the Hundley regime, particularly at the limb. The chromosphere is filled with magnetic field, but it's not as concentrated as it is in the photosphere, and therefore the magnetic field is weaker. So the Hundley effect is I think, a very important part of our ability to understand the chromospheric magnetic fields. One code that I should mention here is the Hundley Rt Code, which was developed by Atanasio Del Pino Alamon and Roberto Cassini at HAO a couple of years ago, which I think has great promise for a combination of Hundley-Zeeman diagnostics. Now, as I mentioned, these kinds of diagnostics are very computationally intensive. So I think that machine learning techniques actually offer great promise to reduce computational load to manageable levels. Of course, machine learning techniques come with their own set of caveats and warnings, but I think this is something that we really need to explore. Now, we have apparently listed here a number of codes and diagnostics that we might be able to use. So the next thing that we now need is some data. For this purpose, I'm going to talk today about two instruments that I've been working on over the last decade or so. It's a little unsettling to put together a talk that's less than an hour that essentially covers the last 10 years of my scientific career. But here we are. So the instrument on the right is the visible spectral polarimeter for the Daniel K. Inouye Solar Telescope. And the instrument on the left, on the top left, is the ChroMasphere and Prominence Magnetometer. These are very different instruments, as you can tell. One of them is a slit spectrograph, the other is an imaging polarimeter. They don't seem to have a lot of similarities. And you might actually say, well, you're not being entirely fair here to the visible spectral polarimeter. In fact, where is this thing? Well, it's actually in the Coudet lab of the telescope. It's over here. And the light's coming up from over here, coming down, and it feeds not only the ViSP, but also a suite of other instruments in the same lab. Now, you might say, well, that's not entirely fair. Where's ChroMag going to be? Well, it's going to be on our solar pointed spar in Mauna Loa at our observatory that HAO operates on the Big Island of Hawaii. And so maybe this is a fairer comparison. Well, not really, because we're not including the telescope that's feeding the ViSP. So here is the DKIST. So DKIST is a very large telescope, obviously, and a very new development. It's only become operational in the last few months. Light comes in over here and bounces off a 4-meter aperture mirror and is fed through a series of relay optics to the Coudet level down here, and ViSP is somewhere over here. I'm not quite sure exactly where in here, but it's on this level where it says Coudet level. If I was to scale both of these two instruments to the same size, physical size, ChroMag would be about this big. So we can see that these are extremely different instruments, and yet they aim to study the same region of the sun and address many of the same science problems. Here's a quick overview of the two observatories, the DKIST on the right and the Mauna Loa Solar Observatory on the left, and you can see that there's a very stark difference in scale between these two observatories. So let's talk about some of the science goals of the ViSP. Here's a list of them, and these are only just a couple of key science goals. I'm not going into very specific science targets here. So these are sort of broad, overarching goals that are aimed to be addressed with ViSP and with DKIST. In particular, this focuses on many small-scale magnetism topics, such as what does magnetic field exactly do in the photosphere? How is it structured there, both in the quiet sun as well as in active regions and in coronal holes? How does it emerge? How does it evolve? And how do active regions decay? There's some questions about the fine structure of sunspots that we've seen very great simulations from Matthias with very high resolution that show all kinds of interesting structure that we haven't been able to observe yet. But presumably with instruments like ViSP and with telescopes like DKIST, we can access these spatial scales. So it's a very exciting thing to be able to observe. Other topics of interest are precursors and triggers of solar flares and coronal mass ejections. I don't think I really need to talk about space weather here, but this is kind of what it's about, research on space weather subjects. And that includes filaments and prominences. Filaments and prominences are really the same thing. Prominences are observed off the limb, filaments on the disk. Other topics are relate to the mass and energy cycle in the lower solar atmosphere and into the corona. Particularly to me, at least, the mass and energy cycle of the chromosphere is very interesting. The chromosphere requires about a factor of 100 more energy in order to stay at its temperature than the corona does. And it also requires a large amount of mass to be pushed up in there somehow. How exactly that happens isn't entirely clear. The connectivity of the non-eruptive solar atmosphere, I think, is also very interesting. We know that somehow all this magnetic field has to connect to someplace. Some of it makes it out into the heliosphere. The sources of the solar wind, fast solar wind from coronal holes and slow solar wind from other regions of the sun are interesting subjects to study, I think. With an instrument like ViSP, we should be able to see the small footpoints of the magnetic field in the photosphere and trace that into the chromosphere by looking at the right spectral lines, and then connect it to the rest of the heliosphere, hopefully through observations from other instruments at DKIST or from other observatories entirely. Now, if we compare that to the ChroMag instrument, we can see that a lot of these science goals are actually very similar, and yet the instruments are very different. One of the key differences between the instruments, though, is that with ChroMag, we're looking more at long-term evolution over periods of solar cycles, 11, 22-year kind of timeframes. We're still looking at emergence, evolution, and decay of active regions. We're still looking at precursors and triggers of solar flares and coronal mass ejections. One of the things that ViSP is not particularly good at, but we'd like to do with ChroMag, is looking at waves. Waves must be very important in heating the chromosphere. We know this. People have done lots of studies on these, but a lot of waves are actually pretty difficult to observe, particularly non-compressive Alfvén waves that only have a signature in magnetic field. We have to be able to capture these waves, and so we need to sample fast enough in order to do that. And then the remaining topics listed here are the same as for ViSP. Again, mass and energy cycle and connectivity of magnetic field. So let's take a closer look at what the visible spectral polarimeter for DKIST is capable of. It's really a research spectral polarimeter. It offers a very high spatial and spectral resolution, and it offers continuous tuning capability over its spectral range. It can observe 3 spectral regions simultaneously. This allows us to select, let's say, a photospheric and 2 chromospheric lines in order to observe those simultaneously and kind of span the volume of the solar atmosphere with a single observation. Its wavelength range is visible and near infrared from 380 to 900 nanometers. This was driven by the desire to observe the calcium lines. There's 2 calcium lines around 390 nanometers, and there's 3 calcium lines around 850 nanometers, all 5 of which sample the solar chromosphere. So those are very interesting lines. We wanted to cover those, and that's where the wavelength range comes from. But it also includes many other diagnostics that we all know and love, like the 630 nanometer lines, and a variety of other lines in that wavelength range that we can study for other purposes, including, for instance, scattering polarization lines, like the barium 4554 line, sodium D lines, and such lines that have interesting polarization signatures. Spatial resolution is very high, but it's not at the DKIST diffraction limit. It's twice the diffraction limit of the DKIST, which equates to about 0.07 arc seconds at 630 nanometers. That works out to like about a 100 kilometer structure on the sun. Spatial field of view is 2 arc minutes by 2 arc minutes square. So that's not a very large field of view, but it's big enough to capture a small active region, or if you really wanted to, you could mosaic something and sample a larger region if you wanted to. Spectral resolution is very good, at better than 180,000. And polarimetric capability, we can get to about 10 to the minus 3 continuum intensity in about 10 seconds. In order to interpret these magnetic fields, we generally need very high signal to noise of about 1,000 or so. So this is a very important metric for an instrument to hit. If you want to know more about ViSP, you can actually go read my paper. This was published yesterday, so still kind of warm off the press. Very excited to have this out and have people start using the instrument. So what are the challenges for designing an instrument that meets these requirements? Well, the first problem is that large telescopes actually require large instruments. You can't take a an instrument from a smaller telescope and put it at a larger telescope with a larger aperture and still get all the same performance out of it. This has to do with a problem that will come back later. Essentially, the issue is that if you have a larger aperture, you need to have a correspondingly smaller field of view. Then the other problem with designing a spectrograph is that the spectrograph design is highly constrained. In the case of the ViSP, our design process was to develop something that would actually fit in the Coudet laboratory in the space that was allowed us to build our instrument within. But at the same time, it also needs to be manageable. Optics need to be manufacturable. So the slit plate scale is driven by the ability to manufacture a slit that has a constant width and a very high aspect ratio of about 5,000 to 1. It has to be long in order to cover the field of view, but it has to be narrow in order to get the spatial sampling in order to hit the spatial resolution requirement. Then one thing that people often don't understand about instrument development is that the choice of your camera is very, very important. Once you've chosen your camera, you now set the magnification required between the slit and the camera because you need to match the pixel size of the camera to the width of the slit or some factor thereof. Then we need to meet the spectral resolution requirement and spectral versatility and continuous wavelength coverage. That requires careful selection of the grading. These things all together essentially drive your spectrograph to look in a particular way just based on the requirements. There isn't a lot of choice left after you've gone through all these exercises. The other thing that we wanted to do with ViSP is have an automated setup. It's very difficult to actually get into the Coudet laboratory. It's a clean room, so you have to be suited up. And there's a lot of other instruments in there that people also want to use. In order to optimize the time usage of the telescope, it's important that we can set up the instrument remotely without significant amount of manpower and without access to the Coudet laboratory. And therefore, ViSP is very highly automated. Now, for an instrument that meets these requirements, there are a couple of other solutions that you might choose, but we chose a traditional slit scanning shell spectrograph. It has a library of photo etch slits, so we can select the width of our slit to match the diffraction or twice the diffraction limit of the telescope at various different wavelengths. Because of cost, we wanted to select a off-the-shelf grading, which we were able to find and use. And the instrument is very highly similar in the 3 spectral arms that it has. Here's an optical rendering of the system. There's 3 feed telescopes down here that take the light feed from the telescope and make an image at the slit over here at point 2. Most of the light actually reflects off the slit and is captured in a beam dump over here. Some of the light that passes through the slit then goes through a polarimetric modulator, which is important for making the polarization measurement. This is essentially one part of the system that encodes the polarization signal into intensity. It then bounces around in order to stay compact enough to fit in the room, goes through a collimating lens, falls onto the grating, and is dispersed into the 3 virtually identical camera arms. Those camera arms at the back end have a polarizer, and the polarizer is the component of the polarization analysis system that actually copies the polarization signal into the intensity that the detector can then measure. It's fairly large. You can see the scale down here. 1 meter is about this big, so you can kind of figure out this is roughly the size of a small room. Here's a mechanical rendering of the instrument where we can see the feed mirrors over here. So the light is essentially coming in from over here, bouncing off this mirror, that mirror, and onto the slit, and then into the spectrograph from there. A picture might show you a little bit more. Here is a picture from inside the Coudet laboratory that we took, I think, before the pandemic. A lot of the work that we were doing was temporarily stopped when the pandemic began, and some of it had to be done during the pandemic, which was an interesting challenge. You can see in the foreground here the third camera arm, then the second camera arm, and the third camera arm back here. You can see the grating over here, and one of the feed optics elements is over here. Here's a view towards the slit plane. You can see we're actually projecting light onto the slit now. This is coming out of the telescope. There's a light source in the top of the telescope that can send a beam of light with some information like a target or some sort down into the Coudet laboratory that we can use for our alignment. Here's another view of the three camera arms. You can see they're very similar. You might notice that the lenses are square. There's a very good reason for that. Square lenses are much harder to manufacture than round lenses, but in order to get the best spectral diversity, we want to be able to position the camera arms as close to each other as possible. So a round lens would waste a lot of space around the arm, and that would not allow the other arms to approach quite as close. The same goes for the collimating lens over here, which is also made square so that the first camera arm can butt up almost completely to the collimator. And this is really a key aspect of ViSP that gives us the spectral diversity or the wavelength diversity that we desire to have. I hope this movie works for you all. Here's a kind of a look around the instrument as it was nearing its completion. It isn't quite complete here, but it's mostly together. So we can see the three camera arms over here and the collimator lens over here. What's actually happening here is that the Coudet laboratory as a whole is rotating, and I'm standing still taking this video. This allows us to compensate for the rotation of the image that's introduced by the alt-azimuth configuration of the telescope. So let's talk a little bit now about the chromosphere and prominence magnetometer, ChroMag, and how it's different. So ChroMag is a more synoptic instrument than ViSP. ViSP is really intended for specific studies of specific active regions or specific areas on the sun. ChroMag is going to essentially take a constant data set continuously of the whole sun. It's not going to, it can be adopted to specific research projects, but there will be a synoptic program that we run every day, at least every day that we can observe. We have 5 spectral lines, so instead of having the continuous wavelength coverage, we only have a specific selection of lines that we've predetermined. We've decided on a photospheric line, iron 617.3. This is the same line that HMI uses. Then we have 3 diagnostics of the chromosphere, the well-known hydrogen 1 H alpha 6563, and then this calcium line that I already mentioned that was a design driver for ViSP. We also have access to the helium 110-830 line. This is at the very edge of what you can observe with a silicon detector. But fortunately, this line is pretty bright, so it actually seems to work pretty well. We also have a helium line for prominences that is really not very useful on disk, but for prominences off the limb, you can get some very interesting information in this. Spatial resolution is much worse than ViSP, 2.5 arc seconds, but we have a much larger spatial field of view. Of 1.25 our sun, so about 2.5 solar diameters total. In polarimetric capability, ChroMag is much faster. This might not look like it is based on this metric here, 10⁻³ continuum intensity signal to noise in less than a minute for 3 lines. Recall that ViSP had 10 seconds here, but remember that this is actually viewing the entire sun rather than just a one-dimensional line of 2 arc minutes long. So if we want to observe a region of the sun with high cadence, ChroMag is much more powerful than ViSP. So what are the design challenges for an instrument that has these requirements, and how does that compare to ViSP? Well, I mentioned before this problem of étendue. Étendue is essentially the product of the telescope aperture and the field of view. In the case of ViSP, we have an étendue problem in that the aperture of the telescope is very large, and therefore we need a large instrument. In the case of ChroMag, we have a smaller aperture but a much larger field of view, and therefore we also have an étendue problem. Secondly, ChroMag sees the entire sun. The ViSP instrument only sees a 2 arc minute field of view, So most of the sunlight is actually rejected before it gets to the instrument. In ChroMag, that's not the case. It has to all go through the instrument and get to our detector. Mostly because of the wide field of view that we desire, we selected a wavelength tunable imager design based on the LEO filter. LEO filters are very nice because you can wide field them and make them to first order insensitive to field of view effects. You can't do that with a spectrograph. In principle, you could make spectrographs that work over very large fields of view, and people have done this. But in order to raster large areas very quickly, you have to either have very many slits or integral field units or things like that. And these technologies are certainly possible. One of the recently selected MUSE mission, for instance, the recently selected MUSE mission, which is a solar physics or heliophysics mid-X mission by is going to have a, I think, 37 slit spectrograph in order to raster areas very quickly, but it still isn't going to be as fast as a wavelength tunable imager. One of the advantages of wavelength tunable imagers is that you don't have to observe every wavelength. You can observe only those wavelengths that you want to see. So you might choose to, for instance, sample very sparsely in the wings of lines and more finely in the cores of lines, whereas a spectrograph is going to give you the same spectral sampling with wavelength or through the entire line. So LEO filters are periodic in wavelength, which means that if we have a transmission peak at some wavelength, then some delta wavelength further and before, we are also going to have a transmission peak. So we must select lines and have specific pre-filters to reject the orders that we don't want to see of the LEO filter. So this is why we selected these 5 lines that I've mentioned in the previous slide. Now, the beam through the LEO filter should be collimated, because if it's not, then it degrades the spectral resolution of the instrument. There are some angle of incidence effects still in LEO filters, so we wanted to have a collimated beam through our LEO filter to reach the highest possible spectral resolution. On the other hand, the beam through the order sorting filter, the one that rejects the orders of the LEO filter that we don't want to see, should be slow, which means it has a low angle of incidence, and it should be telecentric to eliminate as much stray light from the unwanted orders as possible, and to have a constant transmission profile over the field of view. Now, the next problem is that LEO filters are temperature sensitive. This is effectively just caused, LEO filters are constructed out of polarizers and birefringent crystals, and the birefringent crystals have the thermal expansion coefficients. So if they expand, then their properties change, and this changes the filter pass band. So we have to somehow correct for this. In our previous designs, we had tried to stabilize the LEO filter very carefully. And while this is to some extent possible, it turns out that at least for a LEO filter with a spectral pass band as narrow as ours, it becomes very difficult to create a thermal design that meets the requirements, and therefore we recently modified the LEO filter to have temperature compensated tuning. Finally, ChroMag has an image stabilization system, and that's because LEO filters are polarizing elements. So remember that I mentioned that the polarization measurement system essentially consists of 2 parts: a modulator that encodes the 4 elements of the Stokes vector in a way that a single polarizer can be used to infer from up to 4 or more measurements the full Stokes vector. In the case of ViSP, we can use a trick. It's called dual beam polarimetry, where we analyze the polarization in 2 orthogonal directions, that is to say, plus and minus q simultaneously. The benefit of this is that any kind of crosstalk from intensity into the polarization measurement, for instance, because of atmospheric seeing or other effects, appears with the same sign in those 2 measurements. But the polarization signal is orthogonal or inverse in those 2 measurements, and therefore, once you subtract the 2 measurements, you're left with only a polarization signal, and at least to first order, the intensity crosstalk signal disappears. Because a LEO filter starts with a linear polarizer, you can't do this because you've already analyzed your polarization signal with a single in a single direction, namely the direction of the entrance polarizer of the LEO filter. So an instrument like ChroMag is actually very sensitive to seeing effects, and therefore adding an image stabilization system is really crucial in creating or producing data of high quality. Here is the ChroMag optical design. Other problems that we have with, as I mentioned, is the thermal problem with all of the sunlight coming in. Therefore, there is a heat rejection filter right at the entrance of the instrument, which then goes over here, and the tip tilt system is over here. This is the part that stabilizes the image. There's a pointing system sensor over here, so we split off part of the light to determine the motions of the image that are then fed back to the tip tilt system. It then folds, and an image is created over here very close to our order sorting filter. So this is a telecentric image, and telecentric image means that every point in the field has the same cone of rays, and that means that the order sorting filter for every point of the field has the same transmission. That's very nice for data reduction, but it's not what we want for the LEO filter. Remember, we want that beam to be collimated, so there's another lens over here that creates a collimated beam through the LEO filter, then a camera lens, and then onto the detector. So comparing these two instruments, ViSP, as the slit scanning spectrograph, is wavelength versatile. We can tune to any wavelength that we want, and we can do 3 regions simultaneously. It has very high spatial resolution, 18 times higher than what ChroMag will have, and it has high spectral resolution, about 4 or 5 times higher than ChroMag. ChroMag, on the other hand, is a very large field of view, 18 times larger than ViSP. It's not coincident that these two, that the spatial resolution and the field of view essentially are traded against each other with the same factor here. The instrument is also very fast, scanning through one line, through 4 lines in less than a minute on the disk of the sun. ViSP, on the other hand, is a very small field of view and is pretty slow. The slit scanning spectrograph is traditionally a very slow instrument. ViSP, because of its very high spatial resolution, is slower than most. If ViSP were to scan its entire field of view with a typical integration time of a few seconds, it will take many hours to actually scan the entire field of view. So ChroMag, with a 1-minute cadence for 4 lines, is actually very, very quick, and that allows us to study wave phenomena that are not really accessible with an instrument like ViSP. The downside is that we have to pre-select the spectral lines that we want to observe, and of course we have slow or less spectral resolution as well, and we have really pretty low spatial resolution, certainly compared to ViSP. So these two instruments are, I think, both very important in where we're going with our science of the chromosphere. On the one hand, we need to study the very fine details with instruments like ViSP, and on the other hand, we need to study fast processes and long time scales with instruments like ChroMag. Now, you might wonder, wait, haven't I heard you talk about ChroMag before? And you almost certainly have. This is certainly not the first talk I've given. As I mentioned earlier, this has been about 10 years of work or so. In about 2012, ChroMag looked like this, or rather, I should say, we built a prototype instrument. We knew we probably weren't going to get everything right, so we decided to build a prototype to kind of test a lot of things, particularly thermal control, tuning the LEO filter, and things like that. About 2 years later, it looked like this. Already at that point, we'd realized that the thermal control was a really big problem, and we built a new backend for the instrument to control the temperature of the LEO filter better. And that actually produced some results. We were able to take some data. We took this data from Boulder, so we never really expected to get very good results, but we did notice that the seeing was a problem, and that's what motivated the choice to include a tip tilt system. You can see on the top right here, this is taken in the core of the calcium 8542 line. You can see how much image motion there is. An image stabilization system really is going to help to stop that motion and freeze that, and that's going to really improve the accuracy of our polarization measurements. Then down here, you might notice that about a third of the sun is missing. It did fall on the detector, but it was not usable because the optical system was very simple. It was, instead of this folded design that I showed earlier, it was a linear design, much more compact, much shorter. But the problem was that the order sorting filter over here saw a range of incidence angles of the beam that fell onto it, and that caused part of the field of view to have too much leakage of unwanted orders of the LEO filter. So we had to change the optical design. This motivated the change to the folded optical design that the instrument has now. So ChroMag has gone through a lot of changes in those years, and of course the pandemic has slowed us down a little bit. This picture is actually from about a year and a half ago, I want to say, and this kind of showed the first view of the ChroMag backend as it's going to be. It looks a little bit more filled in now with optics. There's a lens here. This is the one of the first lenses. There's a lens down here. You can't quite see it in here, but there's a filter wheel over here, and the LEO filter, the big black thing, is over here. In the next picture, we have a slightly better view of the LEO filter over here, and the tip tilt system is over here, and into a sensor system over here. So ChroMag is in its final stages of construction, but ViSP is actually working. So I'd like to show you, as the last few minutes of my presentation, some of the first data that we took with ViSP a couple of months in April, I should say, actually, of this year, or last year, in the science verification campaign, where we observed a small active region. This is actually towards the limb, so the limb is on this end over here. You can see the position in arc seconds. The sun was about 965 arc seconds in diameter, I believe, at this time. So we're fairly close to the limb. You can see in this column line cores in 630 nanometers, and the two calcium lines here, calcium 2, the UV calcium H line, and the 8542 line. On the right here, I've also included a photospheric, or as close to the photospheric image as I can produce within the wavelength range that was captured. And you can see the large differences between these observations. One thing of interest to note is that the 8542 observation looks like it has much better spatial resolution than the UV calcium observation. I think this is probably due to atmospheric seeing is much worse in the UV than it is in the infrared. So you can expect to, under the same sampling conditions, to see higher resolution in the IR line, and I think that's what we see here. Nonetheless, this calcium data in the UV, I think, is very interesting because the line samples higher heights in the chromosphere than the 8542 line does. Of course, we have full Stokes spectra for these observations, and here is an example of one of those. This is actually not the full spectral field of view of this, but just a region that is, kind of interesting. It shows in the center here the two iron lines, and I think this is a silicon line. I forget exactly what these are. It shows a host of lines around these two iron lines in this wavelength region. This line is kind of interesting. This is a titanium line, which is much stronger in the cooler sunspot than it is in the quiet sun around it. Give you an idea of the performance of the instrument. This is after calibration, showing two regions, one with a fairly strong polarization signal of about 20% or so in Stokes Q and Stokes V, showing again the very traditional Zeeman profile. It's anti-symmetric in Stokes V and symmetric, mostly symmetric in linear polarization. On the other hand, we have a quiet region that shows kind of the noise level of the instrument to be about a part in or about a 10⁻³ of the continuum intensity. So these kinds of data we could process through inversion codes and derive results, quantitative measurements of magnetic field, in this case in the photosphere. If we were to apply advanced inversion techniques to the calcium lines, we would be able to find chromospheric diagnostics of magnetic field and other plasma parameters. Here's just a little example of a fairly simple analysis that I did where we determine the azimuth angle of the magnetic field from these Stokes profiles. think that was all I wanted to talk about today, so I'll be happy to take some questions.
Thank you, Alfred. Does anyone have any questions? You can either raise your hand or type them into the chat. Holly, go ahead.
Yeah, Alfred, thanks. Great talk. Do you when is DKIS going to be providing scientific data? And I just want to point out that, again, congrats to both you and Roberto for ViSP being the first one to get through verification. But when are they going to be providing scientific data to the community?
I'm the wrong person to ask. I'm just kind of browsing through the list of attendees here to see if I can put somebody on the spot.
Yeah, that's okay.
I don't immediately see somebody. So they did start science operations in November, I believe. I'm not sure how much they got. The observing season or the winter observing season is, let's say, variable. So I'm not sure that they really got any science quality observations so far. But yeah, they are in their first operational season, and that's ongoing. So as they get data, they'll make that available to the people that put in the applications or the proposals and have telescope time granted. Actually getting the data, I'm not quite sure when. I think it becomes publicly available 6 months after it's been distributed to the proposers.
Okay, great, thanks.
No, thanks, Kevin. Kevin says that the first DKIS operations commissioning observations started just this month. So it's been fairly recent that they've just started that work.
I think Roberto just was ahead of Phil in raising his hand. So Roberto, do you want to go ahead?
Well, just curious, what's next for ChroMag? What is the next step before deployment?
Yeah, so the next step for ChroMag is, let me see if I can pull up a slide that has some information about that. I guess I don't have one in here. This one will maybe do. So the tuning of the filter requires us to drive particular voltages to the liquid crystal devices that are inside the filter. Essentially, you can see the LEO filter as 6 independent filters that are stacked on top of each other, and we need to tune each of these filters to the right wavelength. So we need to figure out what are the voltages that we need to drive these with to get to particular wavelengths. In order to do that, what we do is we take the system. You can't quite see it here, but there's actually a lamp light source set up over here that shines light into the instrument. It goes through the entire optical path through the LEO filter, and then it comes out through this line over here, which is a fiber that feeds into a Michel spectrograph. And we look at the transmission profile of the LEO filter as we drive different voltages to it. So we're going to use this approach to calibrate the voltages that we need to drive to get to specific wavelengths. And we need to do that as a function of temperature. So this calibration is the next step for ChroMag. And once that's completed, ChroMag will be deployed to the MESA lab for testing purposes so that we can make sure we have an instrument that works properly before it goes out to the Mauna Loa Solar Observatory.
So that's the calibration technique that you developed, and it was also used for comp, right?
Yes, exactly. So one of the things I didn't mention here is that between this phase of ChroMag and this phase of ChroMag, we actually kind of rebuilt the filter. This was the original layout of the filter as shown here with the thickest stage at the end. That turns out to be a bad plan because the thickest stage is the most temperature sensitive one. So you want that to be as close to the center of the body of the filter as you can have it. So I actually took the thing apart, moved that stage and moved some other stages around. And then we developed this, I developed the technique to calibrate the filter. Previously, what we did is we calibrated individual stages, and then after integration, there was usually some temperature changes, so we had to kind of fudge the calibrations a little bit. My technique instead allows to calibrate the filter after it's been integrated completely. So that has some benefits to, for that purpose. And it also gives us a way to fairly easily compensate for actual temperatures of the filter rather than just calibrating at a set temperature.
Phil, you have a question? Go ahead.
The ChroMag really looks like a wonderful instrument for space weather applications. So that what I mean is that in the event of a flare and or CME ejection, particularly from a prominence or filament, you should then be able to follow that thing through with the K-core instrument and maybe even the Cosmo instrument if and when that's funded. So what particular design challenges did you have in building an instrument that was capable of observing accurately, flare intensities and what the wavelength range of each narrow band filter is for your ChroMag instrument?
Yeah, so the flare intensities turns out not to be that big of a problem because at least in the visible wavelength region that we're looking at, even a bright flare in H alpha isn't that much brighter than H alpha normally is. This really starts becoming a problem when you go further into the UV in particular. So from that sense, it wasn't too hard. One of the challenges is to get enough what we call free spectral range, which is the wavelength range over which we can tune the filter. And that's essentially determined by the thinnest element in the LEO filter. Remember, I said this filter has 6 stages, and they're all kind of individual filters, if you will. So the one that has the thinnest birefringent crystals in it produces the widest wavelength band, and that sets kind of how far you can tune the filter. And this is important because during flares, we can see very high velocities, and those are Doppler shifts, so that's a wavelength shift, and we need to be able to tune the line or tune the filter far enough in order to see these velocities. So at the same time, we want to get high spectral resolution or high enough spectral resolution, and that means that we need a very long birefringent crystal. So the 6 stages of the filter is essentially determined by these 2 things: the desire to have good enough spectral resolution to still be able to do quantitative diagnostics of our measurements, and at the same time be able to scan far enough that we can capture the high velocities that we expect to see in certain situations like flares. So that was kind of one of the drivers for making the filter look the way it does. Does that answer your question, Phil?
It does, and it just made me think of another one. Over a solar cycle, do you have an idea of how many CMEs and flares you're able to capture with the observing conditions anticipated at observatory?
I'm going to deflect that question to Ben Berkey. I saw he was here. Ben, what's the kind of, how many days a year do you typically observe? About 200 or so?
I think we get data, at least an hour of data, more like 300 days a year. But I don't have a good memory for how much time ChroMag actually needs to be able to produce this and actually see a CME. So 200 might be a better.
Right. So essentially, it's a game of chance, right, Phil? I mean, we're playing the lottery here, and we're hoping that we're going to get lucky at some point. Part of the reason for having a synoptic instrument is exactly this: that if we had specific programs to see flares during specific observational periods, who knows that you're actually going to hit one. A synoptic program that always has the same data products, the same observing program, as long as you tailor that to all the things you really want to see, eventually you're going to get lucky. So I couldn't tell you an exact number. It'd be interesting to kind of do the math on that and figure out how many it would be, but I would imagine in K-core captures CMEs fairly regularly. ChroMag probably will have less observing time per day where the conditions are good enough to observe. So you can look at how many CMEs K-core and CMEs K-core sees, and maybe take half of that or so, and that's more or less how many flares ChroMag is going to see, assuming every flare has a CME associated with it, which isn't true. So I imagine we'll see a fair number, but we're obviously not going to see all of them because we're only going to be observing like 1 or 2 hours a day typically.
Thanks a lot.
Oh, and to comment on your other comment about that this ChroMag really connects very well with the K coronagraph and the large coronagraph in Cosmo. Of course, this is not not by accident. Cosmo is really designed as an observatory, and ChroMag plays an important role in the observatory and is very highly complementary to the other two instruments.
I do not see any more questions for Alfred. So if not, thank you again, Alfred, for a nice presentation.
Thank you.